Today, we're going to talk about Chapter 3's exercise. First, we have the function RUnif. RUnif is a base R function that creates random numbers from a uniform distribution. This looks very familiar because we talked about our binom function last time. R actually has functions to generate random numbers for most of the common distribution. R norm is a very popular one when we need to generate random numbers from a normal distribution. I want to briefly talk about PDF and how to find PDF in R. So DUnit function is a function that we can use to calculate PDF for a uniform distribution. And this function takes on three parameters. 0.3 would be what value X will take, and 0 and 2 would be the minimum value and the maximum value for the uniform distribution. If we run this line, we'll have 0.5, and that is the PDF when X equals to 0.3. So use this as example. I want to make a graph for the PDF of this uniform distribution. As you can see here, when X takes on any value between 0 to 2, we will have a corresponds Y equals to 0.5, which is the PDF. And when X takes on any value that is either smaller than 0 or greater than 2, the corresponds PDF will be 0. Now we run this line. So RUnif 100,000 and 0, 180 to generate 100,000 numbers that follows uniform distribution with minimum value equals to 0 and maximum value equals to 180. And we can find the first 6 and the last 6 of these 100,000 numbers generated, and also the histogram. What should the mean of this random uniform sample be approximately? Let's find the mean here. As you can see that the larger the n here, the closer that this mean will be to the expectation of the uniform distribution. So we talked about this last time. The expectation for a uniform distribution with minimum value equals to 0 and maximum value equals to 180 should be 90. If we decrease the value of n, let's run this again, then we will have a mean that is away from the expectation, which should be 90, right? And if we increase this n, we'll get a mean that is closer to the expectation. See here, right? This number is much closer to 90 than the last number when n is smaller. Sampling distribution is a collection of data that comes from the process of repeatedly sampling from a population. So when we sample from these numbers that we generated, we want to draw a sample of 14, of size 14 with replacement. That means each time when we draw a number, we put it back and we draw another number. So the second number potentially can be the same number as the first one. And each time when we draw a sample of size 14, we can calculate the mean. So this time we have 89.76. Second time we have 97.2. Since this drawing the sample was totally random, so each time the sample mean will be different. Sampling error refers to the difference between a statistic of a sample, like the mean. here, the statistic can also be other things, for example, like median. So sampling error refers to the difference between the sample statistic and the actual statistic of the entire population. Oftentimes, we will find it is very difficult to calculate a statistic like mean or median for the entire population. For example, there's pretty much no way that we can calculate, we can accurately measure the mean of, we can actually measure the mean of all Americans, because Americans are all of the world, and it's always very difficult to accurately measure every single American, right? So the following command calculates the mean for 4 random samples of 14 observations each. So the replicate function here basically repeat whatever is in here 4 times. So here we sample, right? Draw a sample of a size 14 from these numbers, and then calculate the mean, and we repeat this process 4 times. The replication function is something we call the wrapper function. It's a function that hides the work of complex activity. And we repeat this complex activity whatever times that we want. So here, let's repeat this 10,000 times. And now what we have is the histogram of the sampling distribution. So the idea here is it is always hard to find a statistic of the entire population, but it's relatively easy to find the statistic that we care for the sample. So a portion of the entire population. Often it's a much smaller portion compared to the whole population. And we can do this process many times since it's less time consuming and it's much easier to do. So here we do this drawing the sample 10,000 times. And each time we calculate the mean for the sample, and we get a histogram. As you can see, this histogram looks like bell-shaped normal distribution, right? It looks very bell-shaped. We are going to calculate the grant mean from our list of 10,000 individual sample means and compare to our original population mean, so the true mean. When we take the mean of the sampling distribution, so the mean of this thing here, we would get a number of 90.4055. Now let's find the mean of the entire population, which in reality is always hard to do, right? Which is 90.39. So these two numbers are really close to each other. So without calculating the mean of the entire population, what we can always do is to find the mean of the sample means. So the mean, so here we did the mean of our 10,000 sample means to get a number that is very close to the true population mean. Let's look at the summary of the sampling distribution. Now, not only the mean, we also have the median, first quantile, third quantile, minimum and maximum value for the sampling distribution. Now let's look at the quantile for the sampling distribution for the 1%, 5%, 50%, so the median, 95% and 99% quantile. We'll get 5 numbers. Now let's make a histogram where we will add vertical lines for each of these quantile. Now let's look at the bottom 1% of the sample mean. So 1% times 10,000 is 100. So we will be looking at 100 of them. The square brackets are subsetting operators that allow us to specify particular elements of the vectors that we want. I will talk about the square brackets with example. I believe we talk about this for chapter 2's exercise, but I'm going to talk about this one more time. So now we have list 1, right? And if we want the second element of list 1, so we can use the square bracket. So to grab the second element here, which is 2. This is an easy way to use square bracket, but also we can make it a little bit fancier to add logical condition into the square bracket to get our desired outcome. For example, let's say now for list 1, we have 1 to 3, and I want any element that is greater than 2 inside of list 1, which would be 3. So what we can do is to write list 1 greater than 2, right? Which return false, false, true. So the first element of list 1 is smaller than 2, so it's false. The second one is equals to 2, is also false because here we're asking for greater than 2. And the third element is actually greater than 2, which returns true. By doing this, now we are only left with 3, right? So this is the square brackets with logical condition. And now we're going to use this on sampling distribution. So we try to find a sampling distribution with values that are smaller or equal to the 1% quantile of the sampling distribution. So this will also return a logical, this is a logical condition that will return 10,000 trues or false. And then we put this inside of the square bracket. So these are the numbers that are left with values that are smaller or equal to 1% quantile. Let's look at the summary for them. Okay, for exercises, we will deal with this data frame called chick weight. For any data frame or function that we are working on, we can use question mark and then the name of the data frame or function to get some documentation. Okay, so if we want to view the entire data set, we can use view and then the data frame's name. So here is the entire data frame. It's a pretty small data frame with 578 rows and 4 columns. So let's look at the summary, and the summary will give us a summary for each single column of the data frame. The dim function will return the dimension of the data frame, right? The data frame, you can think of data frame as a matrix. So a matrix will have right, 578 rows and 4 columns. One thing really useful for us to grab a column from a data frame in R is use the $sign. As you can see here, if we use the $sign, so chick weight, the data frame, $sign weight, well, weight is one of the columns, right? And by doing so, we can grab the whole weight columns, every single element. And this turn the column into a list of numbers. And we can look at the summary of this column. So we can look at the head, so first 6, right? And we can find the mean. And then we can save. Now let's assign chick weight's $sign weight into this thing. And then we can find the median, 103. Now let's make a histogram of the chicken weight column. And we will also add vertical lines for the 2.5% quantile and 97.5% quantile. You can see here and here. No, this histogram, the shape here looks very not normal, right? It doesn't look like a normal distribution at all. And now let's take samples, draw samples from this chicken weight, my chick weights with size 11, and then we calculate the mean for these samples. We do this for 1,000 times, the replicate function that we talked about earlier. Now we have 1,000 sample means. Each sample mean is calculated by take 11 numbers, right? We can think of this as a population. We take 11 from the population and calculate the mean, and we do it for 1,000 times. Now we have a sampling distribution, right? So we can do a histogram, and what you can see here is this histogram looks like a bell-shaped curve, right? This is follows a roughly normal distribution, which is very different from the plots here. Here, which doesn't really follow a normal distribution. Now we can increase the size of the sample each time we draw. So we did 11 for the last one. Now we're gonna increase the size from 11 to 100. Let's see what the histogram will look like. This looks like even a better normal distribution. Okay, so for exercise 8, we will deal with this data frame called PRECIP. It's basically location with a numeric value associated with it. Let's convert this into a data frame first and assign it to DF. So now we have a data frame with 70 rows on one column. Let's check the dimension. We can view this data frame. Let's make a histogram for this data frame. Again, we have a histogram that does not look like follows normal distribution at all. Let's add quantile for 2.5% and 97.5%. Now we can again sample from the population. So the entire population actually only contains 70 cases, right? And however, we can do 1,000 as a sample size because replacement is set to true here, which means each time when we draw something, we put it back, right? And then we do it 1,000 times, so we will have 1,000 means. So this becomes a sampling distribution. Let's visualize this sampling distribution through a histogram. See something that is very not normal look like. Now the sampling distribution for it does look like it follows a normal distribution, right? Yeah, I just want to say it one more time here. It does seem a little odd to use n equals to 1,000 because there are only 70 cases in the original data set. But since we are replacing a replacement set to true, since we are replacing every observation every time we draw one, so we can draw as many observations as we want. Here is everything that I want to talk about for chapter 3's exercise. Thank you.